Hello, myself Dr. Ramanujam. Today I am going to demonstrate single slit diffraction experiment. The objectives of this experiment are: number 1, to determine the slit width; number 2, to verify Heisenberg's uncertainty principle. Before we get into the experimental part, it is better to understand the background of this experiment. We all know what is the meaning of diffraction. In lower classes, you might have studied light travels in straight line, which is known as rectilinear propagation of light. Whenever an obstacle is introduced in the path of light, what happens is that light bends around the corners, which gives you variation in intensity as shown here. You need to have a light source. Normally it is a monochromatic light source which produces single wavelength light, and you need a screen. To observe diffraction pattern on the screen, we need to introduce an obstacle in the path of light. So here the obstacle is like opaque regions. To observe diffraction pattern on the screen, we need to have a source of light. Normally this is a monochromatic source of light which produces a single wavelength light, and we need to have a screen to observe variations in the intensity of diffracted beam. Of course, we need to introduce an obstacle in the path of the light. If light travels in straight line, if you look at this here, single slit has been introduced as an obstacle. Light can only travel through this region, and hence on the screen the illumination should be between the point P and Q. Above P and below Q there should not have been any intensity variation if light travels in only straight line. But experimentally it has been observed that there is a variation in the intensity, and it has been represented like this. In order to explain the variation in the intensity of light on the screen, the idea of bending of light is introduced, which means light bends something like this. So when the slit here, when the obstacle in the form of single slit is introduced, this part is like opaque part, light cannot pass through this region. So the variation in intensity on the screen supports the bending of light. There are two types of diffraction. One is frontal diffraction, another one is Fraunhofer diffraction. In frontal diffraction, the distance between source and the obstacle and the distance between the obstacle and the screen are as close as possible, which means that we will not be able to get plane waves out of this source. On the contrary, in Fraunhofer diffraction, the distance between source and slit and the screen will be maintained large, so that essentially we get plane waves coming out of the monochromatic source of light, and then the light passes through the slit, and the bending can be realized on the screen in the form of variation in the intensity of light. So what in first part we will be doing is that you will be given a slit of particular width, and that has to be determined through the diffraction phenomenon which we will observe on the screen. If you look at this expression, the intensity of light on the screen varies as I equal to I naught sine beta by beta square. So where beta is related to the alpha angle of deviation, through this relation beta equal to pi d sine alpha by lambda, where lambda is the wavelength of light. You see, this is the single slit, and we get that principal maximum over here. Intensity is maximum because this beam is undiffracted. You register maximum intensity. If you go away from this point, the intensity decreases and it goes to minimum and it starts increasing and it goes to maximum and then it starts decreasing once again, like it increases, decreases and so on. So the variation in intensity can be mathematically written like this: I equal to I naught sine beta by beta square. So we need to find out at what values of beta, rather alpha, we get diffraction minimum and secondary maximums. This is undeviated beam, which is known as principal maximum. This is the first minimum. This is first secondary maximum, second minimum, second secondary maximum. Like that we can also designate here. This is first minimum on the other side, first secondary maximum, second minimum, second secondary maximum, etc. So the distance between the slit and the screen is denoted as B. Alpha is the angle corresponding to the first maximum with respect to first minimum with respect to the central point of the slit, as shown over here. It is also possible that we can find out what is the value of alpha corresponding to first secondary maximum, second minimum, second secondary maximum, etc. So if you look at this expression of intensity variation, when alpha is 0, which means essentially we talk about the undiffracted beam, so the intensity of which is the maximum. You see over here, if alpha tends to 0, beta also tends to 0. So in the limit beta tending to 0, sine beta by beta is 1. So I becomes I naught. So the central maximum always will be having maximum intensity. So now the task is to find out at what values of beta we observe minima and secondary maxima. To know about that, you take this expression I equal to I naught sine beta by beta square, and you differentiate with respect to beta and equate it to 0. What we get is that di by d beta equal to 2 I naught sine beta by beta, beta cos beta minus sine beta by beta square equal to 0. Essentially we are left out with either sine beta equal to 0 or this factor beta cos beta minus sine beta equal to 0. So sine beta equal to 0 gives us beta to be equal to plus or minus m pi. M cannot be 0 because if we put m 0, beta is 0. If beta is 0, alpha is 0, which means we are talking about the central maximum. Beta equal to plus or minus m pi is a condition for observing minimum on the screen. So we know that what is beta? Beta equal to pi d sine alpha by lambda, that is equal to plus or minus m pi. From this it is possible to find out what exactly is the value of sine alpha. Where d is the slit width, lambda is the wavelength of light used, and alpha is the angle of deviation corresponding to, if I take m equal to 1, it will be alpha 1 0, that corresponds to first minimum. The second relation, beta equal to tan beta. If you look at this expression, the right hand side, when beta equal to pi by 2, tan beta goes to infinity. But left hand side is finite, beta is pi by 2. Right hand side, if you put beta equal to pi by 2, tan pi by 2 goes to infinity. So this relation can only be satisfied or solved through graphical means. So to find out the values of beta at which secondary maxima can be realized, we try to plot y equal to tan beta and then superpose on that y equal to beta. Wherever the straight line y equal to beta intersects y equal to tan beta curve, those are the allowed values of secondary maximum. So it is something like this. Here it is shown. We have this how the tan function varies something like this. And nearer to pi by 2, the function goes to infinity. So this is y equal to tan beta, and I have just drawn y equal to beta line. So when this y equal to beta intersects the tan beta curve, you draw perpendicular from that point, you will come to know what is the value of beta, because here x-axis is beta. So if you look at this expression over here, alpha 1 corresponds to the angle at which first secondary maximum can be realized with respect to center of the slit, single slit. So the allowed values of first beta for first diffraction maximum, secondary maximum is 1.435. So what we get is that 1.43 pi is the allowed value of beta. We know that beta equal to pi d sin alpha by lambda. So pi d sin alpha by lambda equal to 1.43 pi. So we get a relation d sin alpha. I will write alpha 1 because we are talking about first secondary maximum. So d sin alpha 1 equal to 1.43 lambda. So I have written over here d sin alpha 1 equal to 1.43 lambda and sin alpha 1 equal to 1.43 lambda by d, where d is the slit width, lambda is the wavelength, alpha 1 is the angle at which first secondary maximum occurs with respect to center of the slit. So here you look at, we get always lambda will be always lesser than the slit width. So the entire factor will be less than 1. So the condition maximum left hand side is a sine function, so maximum it can have the value to be 1. So that we get sin alpha 1 equal to 1.43 lambda by d. Lambda is lesser than d, so always this factor will be less than 1. Hence the general condition for observing diffraction pattern is that the wavelength of light should be of the order of slit width, or the wavelength of light is lesser than the slit width, but it cannot be too smaller than the slit width, as otherwise we will not be able to see any diffraction pattern. So you look at in a similar fashion, we can we get an expression for alpha 2, which corresponds to the second secondary maximum, that is related to lambda and d as given here. Alpha 2 equal to sine inverse of 2.459 lambda by d. So these numbers are obtained from beta equal to tan beta expression, which we obtain the value of beta through graph. So similarly alpha 3 represents sin alpha 3 is nothing but the angle at sine maximum, that is related to d like this. Alpha 1 equal to sine inverse of 1.430 lambda by d. In similar fashion, alpha 2, which corresponds to that of second secondary maximum, and alpha 3 corresponds to that of third secondary maximum. The intensity variation on the screen is something like this, like the intensity of first secondary maximum is 0.047 times the intensity of central maximum or the principal maximum. Similarly, the intensity of second secondary maximum is 0.017 times I naught, which is the intensity of principal maximum. Similarly, I3 is expressed in terms of I naught. The intensity minimum occur at alpha n0 equal to sine inverse of n lambda by d. If we if we concentrate on first minimum, we put n equal to 1. If we talk about the second minimum, we put n equal to 2. So accordingly, the angle of deviation can be represented. So the entire experiment in first part is, if you look at this expression, we need to evaluate d. Lambda is fixed. So some way or the other, we need to find out what is sin alpha 1. You look at this figure over here. Let us denote this point to be y0 and concentrate ourselves on the first minimum. The angle of deviation is alpha 1 0, and the first minimum occurs at y 1 0 prime. Just I denote it. So the distance between the first minimum and the central maximum is denoted as y10, which is essentially y10 prime minus y0. So what I am trying to say is that this distance, by somehow we measure it experimentally, I denote this distance as y10. It is possible for me to find out what is sin alpha 10. For small angle, sin alpha 10 can be equated to tan alpha 10. From this figure, it is possible for us to compute tan alpha 10, which is nothing but y10 by b, where b is the distance between the slit and the screen. So you just substitute for sin alpha 10 in this expression. Sin alpha 10 equal to lambda by d. That's what it is written over here. Sin alpha 10 equal to lambda by d. So substituting for sin alpha 10 from this expression 1, which is y10 by b, what we get is that y10 by b equal to lambda by d. So b is fixed, lambda is fixed, and y10 through measurement, if it can be measured, then it is possible for us to determine slit width. Now the slit width is determined through first minimum. If you want to determine the slit width from first secondary maximum, you take this expression. Exactly in a similar manner, you find out sin alpha 1. As lambda is constant, we need to find out sin alpha 1. This is the first secondary maximum, position of first secondary maximum. This is the angle of deviation corresponding to that. I denote it as alpha 1. So tan alpha 1 equal to essentially this distance. I denote it as y1, which is like always the distance between the central maximum and the first secondary maximum. So tan alpha 1, sin alpha 1 is equated to tan alpha 1, which is equal to, in the second case, it is y1 by b. Right? So what we get for first secondary maximum, we get y1 by b equal to lambda by d. Here lambda is fixed, b is fixed, y1 through experiment we will be able to find out. So d can be calculated. In similar fashion, you go for second secondary maximum. The expression is given over here. And third secondary maximum, you take this expression to find out d. So after finding out the slit width from 3 secondary maxima and one minimum, first minimum I would say, one can find out the standard deviation in d. That is one of the reasons why we compute d from first secondary maximum, second secondary maximum, third secondary maximum and first minimum. It is possible for us to verify the intensity ratios as given over here. This should also be verified. So the first part of determination of slit width deals with measuring the distance between the first minimum and the diffraction maxima with respect to central maximum on both sides. Second objective of this experiment is the verification of Heisenberg's uncertainty principle. I hope you all would have learned this in quantum mechanics class. What essentially it says is that if I represent delta y is the error in the measurement of position of, say for example, microscopic particle such as an electron, and delta py is the error in the component of momentum, then the product of error in the position as well as momentum in the same direction will be greater than or equal to h cross by 2. Or at least one can write delta y, delta py is of the order of Planck's constant. So we need to verify through experiment this relation. This is what the second objective of single slit diffraction experiment. Diffraction experiment is a proof for wave nature of light. We know that light under certain circumstances acts as a particle, and in certain circumstances it acts as wave. So diffraction phenomenon is a valid proof for wave nature of light. In order to explain this, you just consider photons which travel in this direction and just enter the slit. So you see that the intensity pattern on the screen is represented something like this, and we concentrate on the first minimum on both sides, assuming that most of the photon will try to be found within this region. So here if you look at the position of first minimum, this can be understood as follows. You consider the AD, which is half of the slit width, represented as d by 2. So the light rays which come from A, denoted as AC, and BC are approximately parallel. So the path difference between these two light rays, which is denoted as BD, which interfere and causes first minimum on the screen. As it has been explained already, we denote the angle of deviation corresponding to first minimum is alpha 10. If this angle is alpha 10, this angle is also alpha 10. So it is possible for us to find out what is the path difference BD. So you go for sin alpha 10, that is BD by d by 2, or the path difference between these two rays will be d by 2 sin alpha 10. So when the path difference is lambda by 2, we get first minimum. So equating lambda by 2 with d by 2 sin alpha 10, so what we get is that d sin alpha 10 equal to lambda. This is the condition for first minimum. So here before the photons reach these openings, slit, they have momentum only in one direction. If I represent this as to be the x direction, this is to be the y direction, so all photons will be moving along x direction. Once they reach this slit of width d, what happens is that they exhibit a component of momentum along y direction. If p is the momentum of the waves which comes out of the slit at this point C, this can be resolved into two components, and we are interested in y component, which can be written as p sin alpha 10. Essentially we need to check this relation. So we know that delta py is the error in momentum of light in y direction, that is p sin alpha 10. So it is written uncertainty in y component of momentum is delta py, that is equal to p sin alpha 10. Using de Broglie relation, the momentum can be related to the wavelength, using wave particle duality principle, P equal to h by lambda, you substitute over here, so we get uncertainty in y component of momentum is h by lambda sin alpha 1 0. The uncertainty in y direction, which is taken to be the slit width d, because the photon can be here or here or here, anywhere. So the uncertainty in position is taken to be the slit width, and hence it is denoted at delta y is approximately equal to d slit width. So we have found out the uncertainty of position in y direction and uncertainty of momentum, y component of uncertainty in y component of momentum. Just you find the product of these two. What we get is that delta y equal to d and delta py is h by lambda sin alpha 1 0. But we know that d sin alpha 1 0 is nothing but lambda. So for d sin alpha 1 0 you substitute lambda. So lambda goes off. So eventually we are left up with h. So what we need to here find out, we need to check whether we take this expression, we need to find out some way or the other sin alpha 1 0, the way we did in part 1 of this experiment. So this distance is represented with respect to central maximum as y1 0. Tan alpha, this is the distance b as explained before. So tan alpha 1 0 equal to y1 0 by b. Therefore alpha 1 0 is written as tan inverse of y1 0 by b. So delta y delta py is equal to d by lambda sin alpha 1 0 is tan inverse of y1 0 by b. This should be of the order of 1. So here all parameters are fixed. You will be given three different slits of slit width, different slit widths. So d is fixed, lambda is fixed, b is fixed. Only we need to find out measure y1 0 as explained in part 1. If you look at this expression, if we want to make uncertainty in y component of momentum to be less by making the slit width to be less, then delta py will increase. Remember, delta py is related to alpha 1 0. Alpha 1 0 is nothing but the angle of deviation. If delta py increases, which means that alpha 1 0 will also increase, so which means the pattern will be more broader. Right? So what it means is that if you decrease the slit width with the aim of reducing uncertainty in y component of position in y direction, then we eventually see the broad diffraction pattern. This is true even from the expressions which we got for different diffraction maxima in part 1 of the experiment. Say for example, we got a relation sin alpha 1 equal to 1.430 lambda by d. You fix lambda is constant 650 nanometer in our experiment, and if I decrease the value of d, what can happen is that the left hand side alpha value will increase. So eventually if alpha value increases, instead of first minimum to appear at this point, so the pattern will be more broader, so hence you get the angle of deviation to be more, keeping other parameters fixed. So essentially in part 2 of this experiment, verification of Heisenberg uncertainty principle, we have to confine ourselves only to first minimum on both sides. We don't need to find out the distance between secondary maximums with respect to central maximum. No need. Only we need to find out the position of first minimum with respect to central maximum on both sides, as we want to check out whether this relation is equal to 1 or not. So this is what all about the theoretical basis of Heisenberg's uncertainty principle and its verification. How these two experiments can be performed will be explained to you. To understand how we can determine slit width through various mathematical expressions. The main aspect in the determination of slit width is that we need to find out these y's, actually distance between the central maximum or principal maximum and the secondary maximums and minimums. So to do that, we just go for the how we can carry out that. For that, like we have an optical ray which is graduated, which is 1.2 meter long. You can see here graduation. As I told you in the beginning, we need to have a source of light. We need to have source of light. Here the source of light is semiconductor diode laser, which gives you an output of red light. So wavelength is 650 nanometer. So the laser, the term laser means light amplification by stimulated emission of radiation. You get monochromatic coherent light beam. So this will be used as a laser source, and this is the screen which will be eventually kept at the end of this optical ray. This we use a photo detector. You can see it is a pinhole detector. You can see over here small opening. We are going to make the light to fall on this opening. Depending upon the intensity of light, we get like current output. This photo detector is connected to current measuring unit, right? So now source and screen part or here. So I just keep the screen at a larger distance at the end of this optical ray. Now we need to introduce obstacle. Rather, you are given a single slit whose slit width is unknown to you. We need to determine this slit width. You can see over here like white line kind of stuff. Those are like, in fact, that is opening the slit. Rest of the sides you will have opaque, and light can only pass through this portion. You can have a look into it, right? So you will be given like uprights. So this one can have like one can keep this slit in this holder. You release this screw. You can look at over here. One thing is that you can adjust using this screw. It can be rotated. You make sure that this is like exactly this axis is parallel to the base. So you tighten it. Then you release this screw, and you look at inside. There is like small projection kind of stuff. So you can't put this slit this way. It will not go in. So always you need to put on the other side where you don't have this kind of block. So what one needs to do is that you keep this upright at 10 to 15 centimeter from the laser source, and then you just try to put this slit inside this holder. By first you release this screw and it goes freely, and then you tighten this. So make sure that this should be tightened so that it should not bend. Before you start the experiment, you just try to see whether this laser beam is falling on the photo detector, pinhole detector. You can see over here, this should also be like this. So light should reach like this, so that this should be perpendicular to the light beam. Now this laser is laser source is connected to the power supply. I just switch on both the power supply. You can see that at the back side of power supply you have a switch to on and off. So what one can do is that one can switch it on. Now you see that red beam comes over there, right? So remember, once the laser is on, you should not show your hand in between, or you should not see by looking at it, because that is very risky. It is dangerous. So always, if you want to do something, you put off this laser and put off this laser and try to work on. You look at the caution is already been written, like you don't look at the laser beam directly, it is very harmful. Always you should remember. So now what you do is that I just switch on both the current measuring unit and laser power supply. Okay. So let us see that what happens. So laser comes. You see laser beam exactly falls on the photo detector, but it is not exactly at the pinhole. Our objective is to focus this laser beam onto the pinhole. So here if you see this, here if you look at, you have been provided two screws over here to adjust the movement of the position of this diode laser, so that you can see, look at the photo detector where you can see that by using these two screws it's possible for us to move the beam up or along Y direction or X direction. Say for example it moves, lateral movement is there, you can go in this fashion also. So first you can try to make this laser beam to fall exactly on the pinhole. So how we know that it has been so when it is exactly falling on the pinhole, we will see the detector output measurement unit will show variation in the current value. So you have like two scales, as I told you earlier, microampere and milliampere range. So when laser undiffracted beam is focused, normally we get maximum current. So one can see in milliampere range. So we try to focus this beam onto the hole. So when it is exactly focused, you see the current value is getting increased. Now you see 23 milliampere. So this is very good. So the current value changes. Just I am going out of that pinhole, you see current decreases. So entire what we need to do is that always we need to, once you focus this laser beam onto pinhole, don't disturb these screws. You have to leave it. Anything we need to do adjustment from the detector side. Now what we need to do, actually we need to go in both ways. You look at this diagram. From central maximum, one needs to find out the position of 3 secondary maxima in this direction, and also 3 secondary maxima over here. So this screen, this photo detector is attached to a micrometer screw. The position can be adjusted. Before you start the experiment, you keep this micrometer screw can go up to 25 mm. So approximately you can keep this at mid value, say for example 13 mm, and then you fix it. Go for 13 mm. So that it is possible for us to go on both sides. Now use these two screws. Now we try to make it focus this laser beam and we see that there is a variation in intensity. Right, because now it gets focused. Always remember, this should be perpendicular, right? The incoming beam. If it is tilted, the intensity could be different. So we need to take care of that. Now I need to introduce an obstacle. Before doing that, now it is said like, here like the beam is focused exactly in the pinhole, there you get like maximum current of that value what we see over here. Before we introduce, like you put it off laser, because as I told you, you cannot show your hand in between. So you put it off the laser, and now you try to introduce this slit. The position of upright could be some 10 to 15 centimeter from the source. Right? You make sure the slit is receiving the beam. The slit is perpendicular. Adjustment can be done looking at the diffraction pattern. So I just approximately I can keep it like at a distance of 10 to 15 centimeter. Let us see what happens when we switch it on. I switch it on. It's better this. Now I just switch on both the current measuring unit and the power supply of this diode laser. Now slit has been introduced. You just see that once you have introduced slit in the path of the light, approximately 10 to 15 centimeters from the source, laser source, you have to make sure that the laser beam exactly falls in the slit. You can have one can see from the naked eye that the laser beam exactly splits into two halves, which means that this is not more focused on one side, which will affect the intensity of the pattern, right? So you see that once light passes through the slit, so we get like beautiful diffraction patterns. I just introduced the screen to show you how the diffraction pattern looks like. You see over here, so you get many orders over here. The central brightest one is the principal maximum, and then on either side the first one is the first secondary maximum, this first secondary maximum, next is second secondary maximum, third secondary maximum. We get like many diffraction patterns. So it is sufficient for us to go from principal maximum to 3 secondary maximum. So this I just take it out so that the pattern falls on the photo detector. So once, remember that we have already adjusted, we have kept the screw gauge to be at 13 mm. So this platform can be moved. So you look at like, now what one can do is that we use this micrometer screw to adjust the central maximum. Exactly, we need to make sure always whenever you want to focus the central maximum onto the pinhole, you just use these two screws and make sure whatever value of current you register over there, it is maximum. See, it is decreasing, so I am going in other way. So just look at, you adjust these two, how much, so you get like so long as you get like a maximum value over there. You can also adjust the position of so you can see that it just goes as the distance. Try to adjust the distance and try to improve the value of this. So you see that more sharp image is seen over there. So try to adjust this. So once it is focused on the pinhole, you get values to be value. So essentially, like what we get is that in milliampere range, that can go up to 4 milliampere. If the distance of this is adjusted, and try to, and also like it should not be tilted, right? So the adjustments have to be done in such a fashion that we get maximum value over there. Now what we need to do is that now central maximum is focused. Now you just look at, when I rotate this, the screw gauge, what happens to the current? Now I move in one direction. So I just move it in one direction. So you see how this platform moves. See? So current starts decreasing over here. So when I go in the same direction, what happens? Current becomes 0. So you just change the, because less current is being generated because we are going out of pinhole. You can see the current value starts decreasing. After some point, you will see it will start increasing. So it starts decreasing, 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 decreasing. Decreasing, 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 decreasing. Then it starts increasing. So this is the point at which the first minimum happens. So you look at this diagram, we have gone from initially this Y0, central maximum of focus as 13 mm. Now we have gone up to the first minimum because current is decreased. The moment I go in the same direction, it starts increasing. So this point is identified as first minimum. So you go in the same direction. Next what we will see is that you will see increase in the value of the current, and it goes to maximum value. In this case it goes up to this point. In principle, maximum values. So after that this will be identified as first maximum, though the value over here is less, but you see you go on doing that. Let's start. So before introducing the slit, you need to adjust these two screws and make sure that the light falls exactly on the pinhole. That make sure that light is made to fall on this photodetector. After that you try to introduce the slit. This can be kept at maybe 10 to 15 centimeters from the light source. You have to adjust the position of the slit in such a fashion that light is received, light is exactly coming through this opening, and you see that beautiful diffraction pattern over there. In order to see, find out the distance of different secondary maxima on both sides, I have kept this micrometer screw reading to be at 13 mm, so that we can go both right as well as left hand side, and try to take the readings. You see now it has been focused, central principal maximum has been focused in the pinhole detector, and the current register is 2.9 milliampere. You can try, once you have focused the central beam over there, you should not touch these two screws. These two screws are used to align this laser source such that you focus the central maximum on the pinhole detector. Once it has been done, you have seen this is the maximum value of current which you can get. Don't touch anything over here. So you go to the detector part and you just use the micrometer screw to move in one direction, so that what happens, this platform itself moves. Suppose if I rotate it in one direction, if the platform can move in this way or in this way, either way the way you just try to rotate this micrometer screw. So now I just move it in, I rotate it in one way. So what happens, you observe what happens to the current, just you observe. So I rotate it, so current decreases, you can see, because we are going away from the central maximum, and try to see that it starts decreasing slowly, you can move it. So when this is in milliampere range, so when it comes to 0 or 0.1, so I can just switch the range to microampere range. So there's less current can be, clearly displayed. You see that still it decreases. I am going in the same direction. It decreases. After that it starts increasing. At this point, if I move further, the current starts increasing. So you identify this point in principle, the first minimum, and go in the same direction. What happens is that the current increases. It increases. So it increases. So this is the maximum current which you can see at this position. Now what we have done is that we have identified the position of first secondary maximum. In a similar fashion, you can keep on moving to secondary maximum and third secondary maximum. You go and identify the third secondary maximum, fix that point, and after that, in one shot, you go in opposite direction to take down the readings of third secondary maximum, second secondary maximum, first secondary maximum, first minimum, and central maximum. This will be, on the other side also in the same fashion you can do it. So this is then just to avoid backlash error. So it is better like you identify first the third secondary maximum, don't take down readings, but from one side third secondary maximum, you start taking readings of first secondary maximum, first minimum, central maximum, and then on the other side first minimum, first secondary maximum, second secondary maximum, and third secondary maximum. Imagine this to be like we have identified this at 13 mm. So we know at which point the current become minimum, how much of how much the screw, what exactly the main scale reading in the screw, micrometer screw, you can see that will give you how much of distance you are moving, right? So that the difference between the reading corresponding to first minimum and the central maximum will give you the exact distance between these two. So once you have done, as I told you earlier, once it has been you have found out like Y10, lambda is 650 nanometer, B you can easily find out D from here because this optical wire is graduated. You can just find out what exactly is the distance between these 2 points, and you will note it down in your observation. I will just show you how the observation table looks like. In principle, you have found out the slit width. So through 3 secondary maximum, in a similar through 3 secondary maximum and 1 first minimum, you can find out the slit width D. So you can represent that as like D1, D2, D3, D4, and we can try to take what exactly is the errors. So this is what you need to do in part 1. Right? Tabular column for first part is something like this as shown over here. You can write the position of secondary maximum, first minimum, and you just go on one side. Say for example, I have identified third secondary maximum on the left. So you just note down what exactly is the main scale reading in this micrometer screw, and then CSR, you note it down, total, you can calculate it. and the current corresponding to first maxima, second secondary maximum, third secondary maximum, it can be noted down. Similarly, right hand side, when you go from one side to other side, the corresponding readings can be noted down. And you take like current corresponding, when you move it in the right hand side, what exactly is the current which is observed when you are at first secondary maximum or second secondary maximum, third secondary maximum. And then take the mean value of current. I naught is the central principal maximum, current corresponding to the principal maximum. So you just find out the ratio of I by I naught, so that one can check I1 by I naught is whether falling as whether I1 by I naught value is 0.047 or not. Similarly, I2 by I naught, it is 0.017 or not. That can be checked. In principle, for minima, you don't need to do that, because for first minimum, you don't need to go for finding out this. Essentially, it has to be very less intensity, rather it should be intensity should be, theoretically speaking, it should be 0. So then what you try to do is that you know what exactly is the reading corresponding to central maximum, that is written separately like y naught. So that value from this value y naught is known, which means we have identified this point, y naught is known. And I want to find out the distance between the first secondary maximum and central maximum. You just take the difference between YL and Y naught, similarly Y naught and YR on both sides, and take the average of those two differences. So essentially what I have taken is that I have found out what is this distance, and also here what is this distance. So you take the average of these two, that will give you Y. Right? So we know that as I told you earlier, sin alpha 1 0, if you go for first minimum, or sin alpha 1, that is equal to 1.43 lambda by d. Y1, so sin alpha 1 is that y1 by b. So what we have found out is that this y is what for first secondary maximum, it is y1. So that value is obtained. You substitute in this expression, try to get the value of d. Similar question, you just take the reading corresponding to second secondary maximum, third secondary maximum, that's it, like that. And then same procedure need to be done. You calculate the value of slit width, right? So that gives you the completion of your first part. As we know, like lambda is fixed. In case I just decrease the slit width. Say initially I have taken, say for example, 200 micron slit width. Now I go from 200 micron to 150 micron slit width. Lambda is fixed, it is 650 nanometer. Right? So lambda is small compared to d. So if you happen to see that when you decrease the slit width, the entire value will be increasing. So which means alpha 1 should be at higher value. So this can be schematically shown as this is your principal maximum. And you go for, this is the case of 200 micron slit. Right? So we had defined alpha 1 is the angle subtended at this point with the center of the slit. This is alpha 1. Now when I decrease the slit width, what it shows is that the alpha value should be increased. So it means that now if I go from 200 to 150 micron, so naturally you get different value of alpha 1. Alpha 1 is increased. Other way to say is that you get more broadened pattern. You get more broadened pattern. So when you try to decrease the slit width, you will always see the diffraction pattern to be more broader. Right? This you need to observe when you carry out this experiment. As far as first part determination of slit width is concerned, it is sufficient we do for one slit. And here you see we have I told you laser source and you have photo detector. This is a diode laser. The lasing action actually is mainly dependent on population inversion. If you happen to see over here, light amplification by stimulated emission of radiation is a laser. You have atoms at energy level E1 and it will be excited to higher energy state E2, and when they come back you register light of the difference in energy is released. When you have more and more number of atoms are made to go to excited state, they return it, you return to the ground state, you just register more photons. The principle behind laser is that we always need to maintain more number of atoms in the excited state. For that, it is possible to introduce a metastable state so that the atoms stays for longer time, and when they come from E3 state to E1 state, you get for a light beam generated. So in diode laser, exactly what it is done is that you have highly doped P and N region, and it's connected it is connected to positive polarity. It is connected. We will be given 3 slits. One slit you have already used in part 1. So remaining 2 slits of variable slit width 150 micron and 100 micron would be given. And don't change that, you adjust that central maximum to fall on the pinhole by making the micrometer screw initially to show the reading of main scale reading of 13 mm. Once you focus the central maximum corresponding to different slit, before doing that you have to put it off, release the screw completely, you take this slit, first slit out, and you put the second slit into it. Don't change the distance, right? And you keep that at 13 mm and check whether you are able to see the central maximum. Then once it is focused, then what you can see, if it is not focused, you can slightly use these screws to adjust. And what you can do is that after that you rotate in one direction. So you identify the first minimum by looking at the current variation and what exactly the reading corresponds, micrometer screw reading, you note it down. You go to first minimum on one side and then you start taking all reading, first minimum, central maximum and first minimum on the other side to avoid backlash error. And you try, so the same procedure need to be repeated for other slits also. So tabular column is something like this. Slit width, we have 3 slits, 3 different slits would have been given, and you need to concentrate only on the first minimum for verification of Eisenberg's uncertainty principle. You don't need to go for secondary maximum. Just on both sides of central maximum, you just try to identify the first minimum and then find out this distance. This is what is being reflected in this tabulation. So you have micrometer screw reading corresponding to first minimum on the left hand side, you note it down. For 3 different slits, you note it down. Main scale reading, circular scale reading, total YL. For each slit, you have to make tabulation. You can have a separate tabulation for 3 different slits. That is, the full reading corresponding to Y0 can be written over here, and also current can be noted down. So when you vary the slit width, you just try to enter the value of micrometer screw, enter the readings corresponding to first minimum on both left and right hand side. So left hand side total reading is denoted as YL. Right hand, in a similar fashion, the right hand side first minimum reading is represented